Okay, Assalamualaikum. Good morning. Good morning. Pula dah. Good evening. Okay. Now it's 9:12 at night on Sunday, 29th of November 2020. Basically, that we are going to go through the what do you call it, tutorial solution. I've given you the tutorial number 3 and 4 for you to do on your own. And now I'm going to give you the solutions, and hopefully that you'll be able to understand with regards to the tutorial questions. And what I'll do is that we'll upload the solutions later, and also the video. Most probably that I will try to upload by Tuesday, I think. I'm going to upload all the videos. Some of them actually I have uploaded, so I still have half which is not uploaded yet. Okay. Everybody try to solve the tutorial question. No.
Saya cuba, sir. Nombor 1, nombor 2. Lepas tu saya tak tahu macam mana dia jadi sign tu, sir.
Betul.
Tak tahu macam mana.
Saya dapat sampai V over je, sir.
Okay. Okay. We'll see. Let's see. Now I'm going to share the solution. Okay. Can you see the slides?
Yes, sir.
Okay. Can you hear me clearly? Because
yes,
I've changed the router, so Unify has came to my house and replaced the router. Please that now it's clear. No, what do you call it?
Lag.
no lagging.
No lagging. Okay.
Okay.
This is question number 1. Determine the Fourier transform of a real and even rectangular pulse with height of V0 and width of tau over 2. Okay. So basically that, let me see. Okay. We have tau over 2. The period is tau over 2 here. Okay. So therefore, you have a rectangular wave from minus tau over 4 to tau over 4. So to make it this an even rectangular pulse. So this is actually can be represented by x of t is equal to V0 rectangular t over tau over 2. So basically t over the period, capital T. So when you want to do Fourier transform, so you set up this equation. So basically that the equation is basically x of f is equal to the integration from minus infinity to infinity of x of t e to the minus 2j pi ft dt. So this is actually the general form for the Fourier transform. Remember?
Yes, sir.
Okay.
Yes, sir.
Yes, sir. Yes, sir.
So now,
Nice, sir.
what is x of t? X of t is actually v. In this case, is v0 from minus tau over 4 up to tau over 4. So you can set up your Fourier transform. X of f is equal to integration from minus tau over 4 to tau over 4 v0 e minus 2j pi ft dt. So this is actually given by this when you do the integration. Okay, and this is actually equal to v0 sine pi f tau over 2 divided by pi f. So this is the Fourier transform of a rectangular wave with height of V naught and width of tau over 2. You got this?
Sir, macam ni dia jadi sin tu sir? Saya dapat sampai eksponen tu je sir.
Sir, betul sir.
That one is you have to go to know your trigonometry formula, right? Okay.
Okay sir, okay.
Right. That one you have to refresh your math. Okay. These your trigonometric functions from a polar form to the sine waveform. Okay. You have to refresh. Try to look at in your what do you call it math textbook. So this is the first one. The second one is also similar. The only difference is that the width is changed to 2 tau. So the same thing. Same thing. X of f is equal to integration from minus infinity to infinity of x of t e to the minus 2j pi f t dt. This is the general formula for Fourier transform. So since the width is 2 tau, so therefore you start from minus tau to tau. With the height also V naught. So this is really x of t equal to V naught rectangle of t over 2 tau. So x of f equal to the integration from minus tau to tau V naught e minus 2j pi ft dt. The integration of this is 0, whether this is 0, so you only live with this one. So this is actually V naught over 2 V naught j 2 pi f e to the minus 2 pi ft minus e to the minus j 2 pi f t. So this is equal to V naught sine of 2 pi f tau over pi f. So you get this. Okay. Okay. So how to get from here to here? You need to start refresh your math, right? Now, if you are given the two pulses just now, and if you add, this question is basically you have one pulse as in Q1, the question number 1, and the second pulse is the question number 2, and you add the sum of these two pulses. So what is the Fourier transform for that? So basically that's what you have is, the question is like this. This is t. You have one with this minus tau over 4 up to tau over 4, and another one you have from minus tau to tau. So you have these two function. Basically you have x1t and the other x2t. So if you have this function and if you sum this up, two pulses, what is the Fourier transform for the sum of these two pulses? So from the linearity property of the Fourier transform, which is if you have a x of t plus b, let's say x1 of t, b plus x2 of t, this is actually become a x1 of s plus dx2 of s. So this is the linearity property for the Fourier transform. So therefore,
Sir, dia jadi S ke F, sir? Dia jadi S ataupun F?
F, Fourier.
Okay.
Okay, Fourier
Equation.
basically F.
Okay.
Laplace is S,
Oh.
where S is equal to
J omega.
J omega. Whereas
Okay.
Fourier
Terima kasih, sir.
is what, 2 pi? No, this is J omega.
Ha. Itu apa?
Okay, so basically this Laplace is F, S, Fourier is F. So using the linear property, so therefore, if you add two signals, then the Fourier transform is also the addition of the two the Fourier transform signal. So y of f is actually x1f plus x2f. x1f, we got it from the first question. This is from, and what x2 of f is from the second question. So the answer is that is the summation of the two Laplace transform. So you got, this is the answer. Okay, you just use the linearity property. Clear?
Ya, sir.
Ah,
Ya.
simple.
Simple.
Now, question number 4, which is determine the Fourier transform of single rectangular pulse or still rectangular pulse and verify that x of 0 is equal to 1 regardless of tau. So this is actually this. You have at minus tau over 2 and tau over 2, and the height is 1 over tau. This the height. Okay, this value. Okay, this 1 over tau, and the rest is 0. So what is the solution? Okay, from the question number 1 and question number 2, you get something like this. Basically, remember x of t of equal to v naught for minus tau over 2 t is tau over 2. This is actually, this is and 0 elsewhere. So this is actually give you x of f is equal to v naught sine of pi f tau over pi f. So this is the Fourier transform of this. So what is v naught? Is 1 over tau. Okay, this is v naught and sine of that. So there is the transform. So you want to prove that x of 0 is equal to 1. So therefore, at f equal to 0, what happened? Is sine of 0 divided by what? Here. Okay. Anything over 0 it will be what we call it, undetermined, right? This for the limit f equal to 0, this equal to 1. Or you can do this alternate solution, basically that the integration from minus infinity to infinity x of t dt is equal to 1 over tau times tau, so equal to 1. Okay. Okay.
Okay, sir. Okay.
Okay.
So now we are going to Laplace transform. This is the table for Laplace transform. Linearity definition of the Laplace transform. You have linearity properties. You have time delay, multiplication, which some of these we are going to use in the question. So basically that this we are going to use, linearity that we're going to use. What else? I think those two. And this one, in the question, this one maybe, this one, a few. So, find Laplace transform and state the region of convergence ROC for A. The Laplace transform of e to the power of 3t ut. So what is the general formula? Basically this. So basically that this is the general formula. X of s is equal to the integration from minus infinity to infinity of x of t e to the minus or plus? Minus st dt. So for this one, if you want to use the long way, this is basically x of t is e to the power of 3t. And from, because it's ut, it means that it's from 0 to t. Because for t equal less than 0, ut is 0. For t from equal to 0 to infinity, the value is 1. So that's why the integration is from 0 to t. So this is actually x of s is equal to the integration from 0 to t of e 3t e to the minus st dt. Okay? This. And this is actually you can get from the here this property. When e equal to the when you transform e to the power of at, then the transform is 1 over s minus a. So in this case, a is 3, so therefore 1 over s minus 3. And where is the region of convergence? Convergence is when this is what? Gamma or lambda. This time. Gamma greater than 3. Because remember this is the full plot. Minus 3 is basically so this is the line of convergence. So this is the convergent area. This is the right of the convergence line.
Sir. Okay. Jadi yang UT tu dia nak bagi tahu dia punya range je ke? Ke macam
UT.
mana?
Okay. remember in the signal function, okay, basically you have two functions. One function is e minus e to the power of 3t, and another one is u of t. Okay. How does u of t looks like?
ut
and
like
what is
that.
e to the power of 3t?
Dia ke bawah.
E to the power of 3t.
Dia macam mangkuk.
Kalau 0 is 1, somewhere here.
Yeah.
So basically it's going up.
Ke atas.
That right?
Betul.
Right? So basically it's like that, right? So
bukan
all
dia
like that.
Tahu betul? Betul. Betul.
So when you multiply these two, what happened?
Convolve.
This part, right?
Yes.
So you get this, right? So that is a function of ut. It's just to cut off this part. Okay?
Yes.
So your integration basically is from 0 to t.
Infinity.
Because from the negative part is 0. So that's why it starts from 0 to t. Integration. So the same thing with this.
Okay.
So this ut, the function is basically that to make sure that the signal at t less than 0 is equal to 0. Okay? So for this one, what is the transform? You go to the table. This one is cosine plus that cosine here. Okay, so this is the one. So S cosine theta, omega sine theta. So this. Okay, so basically that you use this. This is number 9. So I tanda. What I'll do is that this actually you use number 3. This one you use number 9. Okay, from the table. Table 6.1 or 6.2. 6.2. Okay.
6.2.
So this you use this. So you get this. So from here, okay. This is zeros. 0 is at equal to 3 zeros. But this is, we want to, for region of convergence, we have to find from the denominator. So s squared plus 9. So what is the thing? S squared is equal to minus 9,
3.
right?
Yes,
S is equal to minus 9. So this is actually imaginary, right?
Yeah, betul.
What is the real part? What is alpha part? 0, right? I mean the gamma part. 0, right? Because this is actually, this is basically, you get S is equal to plus J omega. So this is actually J omega. You don't have the real part. The real part is 0. So that's why regions of convergence is greater than 0. So basically that if you plot this, you get like that. This is actually square root 9. This is square root minus 9. Because This is actually the gamma. This is the omega part, j omega part. So the region of convergence is this side. Okay, clear?
Clear, sir, clear.
Okay. For this one, same thing. And e to the minus 3t sine 3t. So this one, we use the oh, this one we don't have this, so actually we use the sine just now, number 6. Sine. So basically this is number 6. From number 6, which is omega, divide by s minus a square plus omega square. So what is omega? Is 3 and a is minus 3. So we get omega is 3 divided by s minus 3. So in this case, s plus 3 square plus omega square. So you get 3 over s plus 3 square plus 9. So this actually can be simplified as this, right? Right? Math.
Yes, sir.
Okay.
Sir.
So you get this. So what is the pole? Pole is basically that at 0 and at
-6.
minus 6. So if you draw this, get one at 0 and another one is at minus 6. So you have this and another one is this part, right? So the region of convergence is that the overlapping part. Since you have two poles, so the region of convergence is at the overlapping part. So that's why the region of convergence is gamma greater than 0. Here, this one, from here to there, because it's an overlapping area between the minus 6 and 0. Okay, for this one. Clear?
Yes, sir.
D. Which one?
MR.
Ah.
1 minus B. 1 over O.
D. This one is basically 1 over B minus A times E minus AT minus over B minus A E to the minus B T. This is U of T. This is times U of T. So do you recognize this? This is basically, when you use Laplace transform, this is actually the linearity property.
Laplace transform.
Yeah. Okay. Basically that this one from table 6.1 you use linearity function, and table 6.2 is basically which one? This 3. Okay, because this is just a constant. So this basically you use T. Okay, so that's why you get this, because this one, you see this step, 1 over s minus a is 3, a is 3. So here, so 1 over s plus a for this one, and this one is 1 over s plus b, and this is just a constant, and this can be written as this, right? So you have a pole at a minus a and a pole at minus b. So you take which one is the most right? The most right. Okay. This what it means is that the most right. If you have this, basically that you take the one that is the most right. Right? The one on the side of the minimum. For example, if A is here, B is here, so you take this side. If A is here and B is here, you take this side, B. Whatever that is on the right, the most right. Okay? This is what it means. Okay, clear?
Yes, sir. Inshallah.
Okay. Find the Laplace, find the inverse Laplace transform for x of s is equal to 1 over s plus 2 times s plus 1 square, where the area of convergence is gamma greater than minus 1. So, first, you have to decompose this equation into this form. You have to decompose. So basically that you have to find K1, K2, and K3. So this is how you do it. So this is what you have to study your math. So now from there, so you got this. Okay. So this is your decomposed equation for this. So we want to use the inverse Laplace transform. You go to the tables. You find something similar to this form. For example, 1 s plus 2, this is number 3 from table. This also from number 3. This one, when you have a square like this, which one? Which one? Number
4, sir. Number 4.
No.
Oh, number 5.
This one, number 15.
15. Yeah.
Number 15. So this is number 15. So you get this. Here 2 is minus 2. 1 is minus 1 here. This one is, you have t to the power of 1 e to the minus 1t. So equal to t e to the minus t. Right? And this can be reduced to this. And for t greater than 0, because actually you have u to ut. All this actually you have ut. U of t here. Okay? So that's why it's for t greater than 0. For less than 0 is 0 because of u of t is 0. Okay. If you don't write u of t here, you have to write this. T is greater than 0. If you write u of t, I understand what it means. So you don't have to write t greater than 0. Okay?
Okay,
I
sir.
accept the answer.
Terbaik ya, sir.
Alright?
Thank you.
Okay. Another question.
Hey.
The input to an LTI system is x of t is equal to sine 2t ut. Use the Laplace transform to find the output y of t and its steady state part for a h of t is equal to e minus t ut, and part b for h of t equal to sine t ut. So basically that this is what the question means through this drawing. Basically that you have a system with a transfer function of h of t, okay, the steady state transfer function of h of t, and the input is x of t. So therefore the output y of t is actually a convolution between x of t and h of t. So when you have the convolution, for a Laplace transform, when it becomes a multiplication. So therefore, y of t equal to x of t convolved with h of t is equal to y of s equal to x of s times h of s in the s domain. Okay, in the t domain is a convolution, in the s domain is the multiplication. Okay, now when you know that it's a multiplication of the Laplace transform of xt multiplied by the Laplace transform of the h of t, so therefore you need to first transform x of t and h of t first. So x of t is sine 2t ut just now. So basically that this is given in this is x of t is given, and h of t is that for part A. So from the table, this one actually you have to go to the table. Right? This is actually from the table sine. Sine is number 4. Okay. This actually from the table is number 4. Number 4, table 6.2, right? Is number 4. Okay. So from the table number 4, you get x of s is actually, this is actually, yeah, I mean, right, this omega is equal to 2, So x of s is equal to omega over s square plus omega square, right? Yeah. Omega s square plus omega square. Okay. So this is the Laplace transform for x of x, x of t. So now the transform for ht e minus t ut, this is actually from table is number 3. So you had a is 1, so 1 over s plus a. So this is the area of this is the region of convergence for this. This is basically s equal to -1. So gamma is greater than -1. So this one is s is equal to square root of 2j, square root of -2. So basically this is actually plus minus square root 2j. So gamma is equal to 0, right? So this area of convergence for this one is this side. This, the area of convergence is -1 here. Okay. So what then? Since you have the h of s and x of s, Therefore, so you multiply 2 over s squared plus 4 multiplied by 1 over s plus 1. So you get 2 over s squared plus 4 times s plus 1. So this can be written as this. So therefore, you can use, since you want to find y of t, so you need to use the inverse. So this actually looks like, this is actually is 0.4 times 1 over s plus 1 minus 0.4 over s 4. So this go to the table, this is actually looks e something, like e to minus t, with a 0.4 in front. It's number 4 here. And number 3. So this is actually you use number 3 from the table. Okay. So you get 0.4 e to the minus t u t. For this one, 0.4 times s minus 1 divided by s squared plus 4. So this is actually, go to the table, you try to find which one looks like. So maybe something like this. Maybe number 7. Can it be number 7? To transform this. This can be written as 0.4 s minus 1 over s squared plus 4 s squared plus 4. Let me see. Try. Basically, you need to anyone that looks, or maybe this one. So you need to be able to find which one. So you need to play around with this. Which one? Right? This. Okay? Oh, this one maybe you can split into minus 0.4 s over s squared plus 4 and plus 0.4 over s squared plus 4. Anything that looks something similar to that? This is 1 and this is 1, right? 4 and 5. So this is 5, this is 4 from the table. So basically this one, okay, you break it into this part and this part. So you get one is cosine and other one is sign. So this one is the one that you have S on top is S on top is cosine, right? Here. And the other one is this one. Okay. So you get this. Right? This one is transformed to this, and this one is transformed to that. Then you can reduce this. This way you have to use the trigonometric function to get this. Right? Okay. Either you give this or you give this. Right? This also you get marks, right? Okay. So basically, right? Okay. So basically, you have to review your trigonometric functions. Right?
Okay.
Second part. So basically that the same this. So x of s is still 2 over s squared plus 4. So x of s is 2 over s plus 4. 2 over s squared plus 4. Okay. So h of t is this. So this one you use the to get the Laplace transform. You use the this one. Wait, this sign just now, right? I punya ni I mudah lupa. Sign of t. Sign of t. So number 4, right? We use number 4 from the table 6.2, right? So you get this. Basically omega over s square plus omega square, where omega is 1, right? So you get that. So now it's a matter of multiplying x and h. So you get this. And from here, you have to decompose so that you can write in recognizable form so that you can use the tables. So this is actually this number 4. This actually you use number 4. So number 4 from the table, right? So that's how you do it. So instead of doing the convolution, you are solving the problems using the Laplace transform to get the y of t. Right? Instead of using y of t is equal to x of t convolved with h of t, what you do is that y of s equal to x of s multiplied by h of s. Then you take the inverse Laplace transform. Then you get y of t. Right? This is the type of question maybe will be in the test. Question number 20 and number 8. So this one I take out the part B because this you have not learned yet. Because in the textbook, they what do you call it? It was presented in the form of first part is continuous, second part is discrete for each title. Whereas I teach this class is we go through all the continuous first, then after that for the second part we go all the discrete functions. Okay, so this you have not learned the discrete part yet. The discrete part will be after the first test. The first test is only on the continuous function. Right? So basically that you have A, C, D, and E. Right? So for the part A, you find y of t equal to xt convolved with h of t for the following cases. X of t equal to sine t ut and h of t is equal to e to the minus 0.1 t sine 2t ut. C is x of t, which convolve with basically u of t convolve with e to the minus a t ut, and C is t ut convolve with e to the minus a t ut, and E is 1 over t convolve with the e to the minus a t ut. So this is the solution. Same problem. Basically, just these systems, which is x of t convolve with h of t. So this is x of t. This is h of t. So you use the table. This is table number 4, I think. So you have to be able to, yes, number 4. Number 4 in the table. This one, this is also from the table, right? This e to the minus this sine. E to the minus this sine, so basically number 6. So this is number 6 from the table, right? Then you multiply. So you get this, right? And you need to decompose, right? You need to decompose and find the numerator. So you get this. So from here, you use the, what do you call it? The, what do you call it? This inverse Laplace. So you get y of t. This. You can go through this on your own. So this is the solution. Okay. So this is basically the poles. This is the imaginary pole. This is the complex pole. Now is for the C, same thing. X of S. This one is actually U of T. This you go to the table number. Use 2. Which is transfer, basically becomes 1 of S. So you from the table is number 2. So 1 over S times 1 over S plus alpha. So this can be written as this, and this actually then you use the inverse Laplace transform. This is equal to 1, and this is actually this part. Okay. So yes, you use the tables, right? For TUT, this you go to the table. TUT is which one? Which one? This 14, where n is equal to 1. This is actually table number 14, where t to the power of n, where n is actually equal to 1. So therefore, you have 1 over s square is the Laplace transform here. 1 over s square times 1 over s plus alpha. You decompose, so it can be written. So you get 1 over alpha, 1 over alpha square, 1 over alpha square. So you can, what we call it, use the Laplace, the table to find the inverse Laplace. So you get this, this, and this. Okay. This part is this. 1 over s is this one. 1 over s square is this one. Okay. E x of s is equal to, this is actually from the Laplace transform that that you do for this one, right? So you get this, right? So x of s is basically you get this. So from 0 to t, 0 to capital T is, you can multiply by that. So you get this. And from here, you can use the inverse Laplace transform. So you get this. This part is this, and this part that. Okay. For t greater than that, greater than t, this is the multiplication. Right? Okay. And this actually, then to get the total y is basically that you get the from the first one and the second one. Add. Okay. So therefore, this is actually the function of y of t. For t less than 0 is 0. For in between 0 to t, to capital T is this. And for greater than t is this. Okay. So this one you can go through. But for the test, it will be something easier than this. Just what to call it? You go through and try to understand the solutions. Okay. Any question? Any question? Before I go to the
No, sir.
Before I go to the solution for the tutorial 4.
No, sir.
No, So what I'm going to do is that I keep this whatever that I counting first, I keep. Then after that, I will try to call it post it to you lah, in the MS Team or in the WhatsApp. Okay. So for the second one, the third one is on the frequency response. Can you hear me?
Yes, sir.
Yes, sir. Yes, sir.
Yes, sir.
Okay. I'm going to share the slide. Can you see the slides?
Yes, sir.
Okay. You are given these circuits. Okay. For the test, a simple filter is included. But you don't have to do calculation lah. Just at least you need to recognize what kind of filter is that. So in this question, in the parallel RLC circuits, this is actually question number 16 in the textbook. You are given L equal to 1 millihenry, C equal to 100 nanofarads. You are given IS as the input, and the element the element currents of I1T, I2T, and IT and I3T are measured across the resistor, inductor, and capacitor respectively as the output. So you need to sketch the frequency response in the form of a body diagram. And in this question is where you need to sketch the magnitude and phase of the three systems. Basically that you have H1S is equal to I1 over IS, H2X is equal to I2 over IS, H3S equal to I3 over IS. For each the three cases, R equal to 5 ohm, R equal to 50 ohm, and R equal to 500 ohms. And the question is that and also besides sketching the body plot, you also need to answer what type of filter represented by H1, H2, and H3. So what are you going to do first? First, basically that you need to calculate, you need to write what is the transfer function, H1S, H2S, and H3S. In order to do that, you need to know what is I1, what is I2, and what is I3 in the function of S. So, you use the nodal analysis. Remember nodal analysis? This is your node, and this is your ground. So the nodal analysis that you have how many current here? You have 4 going into the, you have IS is going, you have I1 going out, I2 is going out, I3 is going out. Therefore, apa tu? Therefore, you can write the KCL, right? Kirchhoff current law. So IS minus I1 minus I2 minus I3 equal to 0. So IS equal to, what is I1? Ohm's law, V over R. Because the voltage usually V. So V over R, because this is R here. R, L, and C. So V over R, I2 is basically that V times the impedance of the capacitor. I mean divided by the impedance of the capacitor. What is the impedance of the capacitor? 1 over SC. This is really the impedance of the capacitor. So I is actually voltage divided by impedance of the capacitor. So therefore I2 is V times CS. So this is the current through the capacitor. The voltage divided by the impedance of the capacitor. I3, what is I3? I3 is the current through the inductor. So how you get the current? Basically the voltage divided by the impedance of the inductor. What is the impedance of the inductor? Is LS. Okay. So therefore the current is V over LS. So you substitute into this I1, I2, I3 in terms of V, in terms of the voltage. So therefore IS can be written as V times 1 over R plus CS plus 1 over LS. So this can be written as LS plus RLC S square plus R divided by RLS times the whole thing times V. So this is your IS. So for the H1, it's given as I1 over IS. So I1 is that this is given V over R. So V over R divided by the whole IS. This can be simplified as that. Okay. For H2 is I2 over IS. What is I2? VCS. VCS. Wait let me see. Ada silap sikit ni. I2 is this inductor. Silap. So this is actually I3. This is I2. Right? Okay. So I2 is that. So I buat silap kat situ. So this is actually I3. This is I2. Okay. Okay. So I2 is this. And I3 is this. So from here, you can see that you have 1, 0, and you have 2 pole. So 1, 0, 2 poles. This is a band pass filter. This 1, 0, 2 pole is a band pass filter. This one, you don't have a 0, and but you have 2 pole. What kind of filter is that?
Low pass.
Low pass.
It's a low pass filter. And you have 2 poles and 2 zeros. 2 zeros and 2 poles. So this is the high pass. Now if you want to draw this, given this R value. So basically that you can plug in the value into this equation, this, and you solve for S. So you get this. These are the poles. The zeros basically this 0 is at the origin. This actually zeros at the origin. This one is also zeros at origin. This one actually you have 2, 0. This actually you have 1, 0. This one you know 0. Right? Wait. This is actually with regard to that. No, this is no. This is actually correct for okay. This is actually the first one is for the okay. I erase this. let me put here this band pass, low pass, and high pass filter. For band pass, you have 1 0, low pass 0, no 0, and these 2 zeros just now. Right? Same thing all. Right? So this is the pole for R equal to 5. You calculate, so you get about 1.995 megahertz, and another pole is at 5 kilohertz because you have 2 poles. This is really from here. Here, you have 2 poles for the band pass. This also you have 2 poles. So this one also, these 2 poles is at 0.1 megahertz. Both poles at that. This one, you have the poles at 0.0977 megahertz. And you can draw this. For the first one, h of 1, okay, this A, B, C is actually, this one is 3, this is one is 2, this for R value, this one, this is R equal to 5 ohms, this one is R equal to 50, this is R equal to 50 ohm, this one is R equal to 500 ohms, okay. This is actually to show you the effect of the Q, right? The Q effect. But if you draw the symptotic line, for the first one, let's say we take this one, basically at 1.995 and at 5. 1.995 is about here. This is 1. This is 1 times 10 to the minus 10 to the power of 6. This is 2, 3, 4, 5. Okay, 2, 3, 4, 5. Basically, that you have. Wait, this is 1. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is 2. So basically, that is here. So this asymptotic. This is the asymptotic line at 1.995, and another one is at this 5 kilohertz. Okay, here you have this and this. So, and this line is basically is 20 dB per decade, and this also 20 dB per decade. And remember, for the band pass, you have 1 pole, right? 1 0 at the origin. So basically, it started with 20 dB per decade. Then after that, it cancels out, so it's flat. Then after that, it goes down 20 dB per decade. So that is the band pass for R equal to 5. For R equal to 50, this, from your calculation, you get 2 poles at 0.1 megahertz. And you have 1 0. So this is the orange one, the asymptotic line. So you get the 0, 1 0, and you have 2 poles here. So you get this shape. And the red one is actually, in terms of the poles and zeros, are the same as the it's almost the same lah, because this is actually the exact calculation. You get 0.977 megahertz instead of 0.1. But from this diagram, it's almost the same lah. So I still use what call it yellow one. So basically that you go up and you go down, something like this. So if you draw asymptotically, you get, for the first one is this, that, and goes down. The second one is something like this and go down. And this one actually is something like this one and go down here. Right? Yeah. You start from here. The zero, then the zeros cancel out and add with the additional pole. So it goes down. So this peak is actually due to the damping factor. Okay. So this is the high pass and the band pass. For the H2 is given by this. So H2 essentially is a low pass. Low pass, basically you don't have a zero. You only have 2 poles. So the first one is you have 2 poles. One is at 5 kilohertz, another one is at here. So what happened is that since you have no zeros, so it's flat. It's flat until you hit the first pole, 5 kilohertz. So it goes down 20 dB per decade until it hits the second pole. Then it starts to go down 40 dB per decade. So this one actually should be here. So it's something like that. So I should move here. So basically from here, then it start to go down 40 dB per decade. So this 40 dB and 20 dB here. Per decade. The slope. That is for the first one. The second one is both are at 0.1 megahertz. So basically that it start from 0 flat until it hits 0.1 megahertz. Then since you have 2 poles, so it goes down 40 dB per decade. 40 dB per decade. For the third one, both poles at 0.0977, so it's almost 0.1. So it's difficult for me to draw, so I use the same curve lah. So basically that is represented by this peak. So it's still the same in terms of the what I call it, your body plot. In terms of body plot, you have flat until it hits 0.0977. Since you have 2 poles at the exact location, then it goes down 40 dB per decade. So in terms of body plot, for the B and C is the same. Only when you do the actual one, then you have the peak here because of the damping factor, right? So you should be able to draw that the body plot by recognizing whether you have zeros or not and how many poles that you have. It's like this, you have 2 poles. Right? And you have no zeros because no S on top. In this case, you have 1 zeros at what do you call it, origin, and you have 2 poles. Now we go to high pass. High pass, is basically that you have two poles at the origin, and you have, two zeros at the origin and two poles. So for the first one, basically that you have two poles, two zeros at the origin. So this is the one. You have minus 40 dB here. You have plus 40 dB per decade. And at 5 kilohertz, you have one pole is minus 20 dB per decade. So minus 20 and 40. So basically it started at, started at minus 40, minus 40 dB, at plus 40 dB, the slope, until it hits at the 5 kilohertz, then it's changed into 20 dB per decade, the slope. Then it hits 1.99, and this is actually minus 20 dB, so it starts to become 0. So if you draw this, actually you have minus 40, then minus 20, then 0. Right? So that is for the first one. For the second one, you have two poles at 0.1 megahertz, and also you have two zeros. So the first one is the two zeros, is is positive 40 dB per decade is the slope. Then when it reaches at 0.1 megahertz, it's cancel out because it's minus 40 with minus 40, so it flattened out. So something like this. The actual one, actually the purple one for the B. For the second, for the third one, is at 0.0977. So I just approximate at 0.1. So it's the same thing. So the slope will be minus plus 40 dB per decade. And when it hits there, and it's flattened out because this and this cancels out. Plus 40 cancel out with minus 40. Okay. So that is the body plot for the magnitude. For the phase, that one is not that important at this moment. Next question. This one basically the rest, the part B, I take out. So you just do the part A. Consider the circuit of figure 9.52C with R equal to 500 ohms, L equal to 1 megahertz, and C equal to 10 microfarad. Plot by hand the magnitude and phase of the system function h of s equal to V2 over V1. So first, you need to find what is V2 in terms of the function of S. So you have the impedance of the inductor and impedance of the capacitor. So you have a tank there, LC tank, which is what it means, LC, L parallel with C. So that one you find the impedance of the tank. So it's LS over LC square, LS over LCS square plus 1. Okay, from there. So what is V2? V2 is basically that the impedance of the tank divided by the total impedance. So times V1. So LS over LC S square plus 1 divided by the this is actually I miss V1 here. R plus LS over LCS square plus 1 times V1. So rearrange this equation, you get LS divided by RL C S square plus LS plus R times V1. So finally you get when you plug in the value, you get 200 times s over s squared plus 200s plus 10 to the power of 8 V1. So this is actually the formula for V2. So from here, you can find the H of S, which is V2 over V1. And this is given by this. Okay, 200s divided by s squared plus 200s plus 10s. So this is actually, if you factor this out, so you have on top, you have 1 0 at the origin, and the bottom one is actually you have a pole at this minus 100 plus minus j 10 to the power of 4. And if you use the, what call it, take the magnitude, so you get pole at 10,000 hertz, about, lebih kurang. So basically that you have two poles. You have a 0. You have a 0, 20 dB per decade. So this is actually 20 dB per decade. And you have two poles here. So when you draw, you get that. Lebih kurang. Okay. That is the body plot. Any question?
Setakat ni tak ada lagi, sir.
So basically that you study this thing, and some of them is basically most of them are related to the test, to the topic, which is body plots and the identification of what type of the filter, and Fourier transform, Laplace transform, okay, Fourier series, convolution, and signal and operation. So all are covered in the tutorial 1, 2, 3, and 4. Right? And if you get what I call it tutorial from the other group, you can ask me.
Baik, sir.
Okay. So when you get the question from them, you just email to me. Send to me so that I can look at those questions and the solutions so that I can explain to you.
Alright, sir.
Any question?
No,
Kalau tak ada question, then basically I'm going to end the lecture. Now it's already 10:40, so we have about 1.5 hours already of lecture, lebih kurang lah, 1.5 hours. So you have a lot of materials already to look at, and see you on Tuesday. Wednesday. Okay.
Okay, sir.
Okay, sir.
So thank you, and I have actually 15 students today. So a few not attended. And see you on Wednesday. So whatever that you go through and study, because the test is on the 11th, right?
Yes, sir.
11 at night,
Sir.
8:30.
Yes, sir.
11 of the December at 8:30 at night. The test will be about 2 hours. And us 15 minutes for you to submit. Okay. So thank you and good night.